Okay, so I think it's time to get going here. Hopefully you can hear me and see the slides. And so uh, I just want to review what the end of the semester deadlines are. So classes end on Friday, December 11th. So our last class meeting like this will be December 10th. And then we don't have a final in this class, but we do have finals week. And so you have a presentation and a paper due, and I'll make it due probably on Thursday finals week so I can grade them Thursday and Friday, or at least grade them Friday and the weekend, and then submit grades right near the end of finals week. And so I'll put some pointers up on Canvas so you know when things are due. I put up a homework assignment to help you work on your outlines a little bit and to make sure you have enough resources to do what you want to do in terms of the final project. And so that will give you something to focus on for the next 3 or 4 weeks. So what's important in the final projects and papers is that they're interesting and they're relevant. And so they should be relevant to additive manufacturing and relevant to polymers and composites. But that can be anything from control software to design to chemistry to perhaps additive processes that we haven't talked about. It could be application based, but a powder bed fusion of metal presentation is not going to be as relevant as we're looking for, because of course this class is focused on polymer and composite materials. But I'll put some things up on Canvas. You should pay attention to that homework assignment, and the more work that you do now to get settled and to get your ideas organized, the less of a rush it will be at the end of the semester. So if you're having problems, or I know that things happen, if you're not going to make some deadlines, just communicate with me. The university is a little bit strict about when things have to be submitted at the end of the semester, but there are ways that we can work through any issues that you're going to have or that might pop up here in November and December. So anyway, now's the time to start thinking about how to put a bow on this class and how to finish doing the types of things you want to do and learning the types of things you want to learn as we finish out the semester. Are there any questions or comments out there? Anything that people want to discuss as a group? Otherwise, of course, I'm available for Zoom or questions by email. That's fine as well. Okay, and the parameters are in the syllabus. So if you're confused about what's going on, just take a look at the syllabus, but I'm happy to go through that with you at any time. Also, I have some lectures still that I want to talk about in terms of different application areas, in terms of safety, aerospace, biomedical, things like that. But we're getting down to the last couple opportunities for you to communicate to me what you might like to hear more about. So if I've skipped something that you really wanted to hear about, or if we're not covering something that might be useful to you, just let me know, shoot me an email, and we can talk about it, and I can try and incorporate that as we go on. Also, there are no classes next week, so we won't have lecture on the Tuesday before Thanksgiving. So that's a formal break. And so make sure you pay attention to the calendar. I won't be on Zoom on Tuesday, and so you can apply that extra time to your homework and your final presentation and paper. Okay, those are all the announcements. That's all I wanted to say in general, but now is time to start thinking about the end of the semester so things don't get too piled up here with all the other classes and exams going on, and I know final papers and other classes too. So now's the time to at least sort out your ideas and make a good plan, and that'll help you in the coming weeks. Any questions, comments, anything people want to chat about? Okay, so last time we left off talking about some of the bigger implications of additive. We're going to talk more about that today as well. And so I brought up this collection of articles. So this is a special issue, and you can see the link at the bottom of the page right here. But this special issue is really a collection of papers talking about a bunch of different things having to do with sustainability, energy usage, how we think about what's going on in additive. So these are some of the topics in terms of life cycle assessment, emissions and safety, thinking about energy consumption, sustainability, and also supply chain. And so these are some really interesting things that people talk about. Oh, the supply chain is going to be easier with additive. That is generally true, but it really comes down to the specifics. Or additive is a more sustainable manufacturing technology. Well, that may be true, but you really need to analyze it in detail. And so there's a lot of general statements out there around additive, especially since additive is such a popular hobbyist activity, and there's lots of people across different walks of life that use additive. But it's not necessarily true that for a specific manufacturing situation or a specific technology, that some of these statements hold against traditional manufacturing, or they hold against some industries that are currently developed. So additive, my message is that additive is not a panacea for a lot of the things that we might attribute to additive, but there's a scientific and engineering methodology that we can use to sort through some of these issues to determine, is additive really more sustainable than traditional manufacturing? Or is the supply chain really facilitated by having additive? And so we're going to talk about that because that's been studied. There are papers written on that. And so that's what we're going to discuss through these collection of articles. And so I think we left off here last time. So the use of AM certainly for final parts enables on-demand manufacturing and on-demand changes. So that's really cool, because usually when you make tooling for a specific industrial product, you can make a mold for one specific type of toothbrush. And maybe you use different colors of plastic, but you're making the same toothbrush over and over and over, maybe in different colors. But with additive manufacturing, you can change the design of the product on the fly because, of course, the characteristics of the product or the three-dimensional shape are held in the software, and it's easy to change the design file on the fly. And so this idea of on-the-fly customization or on-demand changes to those parts is something that additive can really do well, but perhaps at the cost of throughput, because you're not going to be able to 3D print toothbrushes as fast as you can injection mold them. And then in terms of on-demand parts manufacturing, if you study, for instance, the automotive supply chain. So when General Motors releases, let's say, the 2020 Chevy Silverado or something like that. And so they're making a new model car. They make and sell that car, send it to the dealership. That's what consumers buy. It turns out that the automotive plant and all the suppliers that make parts for the 2020 Chevy Silverado make a bunch of extra parts. In some cases, up to 1/3 extra spare parts, alternators, wheels, transmissions, even in some cases, engines, windshield wiper motors, alternators, all that stuff. So they make all those spare parts in general in the same year that the car is made, because they're making those parts, so they make some extra. And then they put all those spare parts in a warehouse. And in 2021, 2022, 2023, etc., for 10 or 15 years after the 2020 Chevy Silverado is out on the road, they're drawing down that spare part reserve. Now, there's a lot of interchangeability. It might be that for 5 years in a row, the alternator is exactly the same. And so they don't have to make as many in that year. But in 2030, they're generally not making alternators for the 2020 model year. The 2020 parts were made about the same time as the 2020 vehicle. And that creates a huge warehousing issue and a huge supply chain issue because it costs money to hold on to that part because you've already spent the money to make it and now it's just sitting around until you sell it to AutoZone or send it to the dealership or something like that. Same thing goes for airplanes. Same thing goes for washing machines. So one of the really interesting things about manufacturing that we don't often hear about is all these spare parts. Not only are they sort of not manufactured year after year, they're generally held for a really long time because they're manufactured in the same year that the primary component is made. And so this idea of making parts on demand is really interesting because if you can 3D print, say, a new bracket for your 1995 Subaru, that can be done today because we have the CAD model for all the parts in the 1995 Subaru. And so you can just say, I need this part number, please print me a part. And that's possible. They're doing this a lot for old airplanes and old cars and things like that, where they're reverse engineering parts. But now they're thinking about, okay, I don't have to make all these spare parts at the exact same time that I'm making the original equipment. And so you can ease the supply chain as long as you have the digital supply chain ready. Like if you wanted a CAD model of a certain fender right now for the 2020 Silverado, you couldn't get it because this is not how it's done right now. Or you can't get a SolidWorks model for one specific bracket on a 2010 Ford Fusion or something like that. But as the additive manufacturing supply chain spools up, and as the digital supply chain starts to gain a foothold, Home Depot or AutoZone or these other places might just have a bunch of additive machines and a bunch of raw materials in their store. And then you dial up the part, you say, I'd like this part, they print it for you, and you pick it up the next day. So that's the future. That's what the Navy is working on right now for putting 3D printers on ships, or what the military is doing for forward deployment of 3D printers in remote operating bases. They basically send raw material in a printer, and then they can print what they want, or they can print parts on demand, so they don't have to take a spare of everything. So that's really interesting, and that's the future of what people are thinking about in terms of this issue of AM-enabled supply chain practices. So that's a lot of jargon, but for people that are interested in industrial engineering and supply chain, there's lots of really interesting things that might be able to happen. So you don't have to transport as many parts. So you don't have to make all the parts in Detroit and send them out all over the country. You can make 3D printers, and then those can be distributed along with the raw materials, and then people can print whatever part you want. Because sometimes you go to AutoZone and say like, well, I would like an alternator, for my 2002 F-150, and they're like, oh, we don't have one. Let me get it in from Altoona, or there's one in Pittsburgh. Let me have them ship it here. And so the parts go out to where they think they're going to be used, but those parts get shuffled around. And so that's more transportation costs. That's more of an impact on transportation on the environment. And so that's something to think about. Reducing material consumption, because there's always overproduction. There's parts sitting around. Those can be a gold mine in terms of new old stock sometimes, but they're also just sitting there not doing anything. And so they cost money just by existing and not being used. Extending the life. This is really important, especially for unique hardware like classic cars or special military components or airplanes that, in some cases, you don't have any spare parts. No spare parts are made, or all the spare parts are consumed. And so you have this thing that you would like to keep working. And this occurs a lot for industrial machinery, and there's no spare parts at all. Sometimes you might not even have CAD files. And so in some cases, they'll take a broken part, they'll CT scan it, they'll re-engineer it, and then they'll print it. And so that's very valuable. And then as we learn more, you can do improved design replacement. So not only do you get the same old alternator that's always been put on that specific truck, but you might get a new and improved part as we learn more about that. So this is discussed in this reference right here. And this sort of gets into the weeds and away from materials a little bit. But other than thinking about material science issues like strength, what type of plastic, what type of reinforcement, how is it failing, what is the dimensional stability, things like that. These are some of the wider issues that you may encounter as you think about additive and as you think about industrialization of what we've been talking about in this class. And it's worth at least pondering as you progress in your career. So we had to cut the discussion short last time because I wanted to end on time to make sure that our colleagues online have a set start and end time for the videos. But Eddie brought up this question last time about what parts are we talking about here? Are we talking about small parts? So a small part might be on the order of 1 kilogram, or let's say 1 liter. So that's a small part, something that fits on a desktop, something like that. Or big parts, this might be on the order of 10 to 100 kilograms. And let's talk about 1 meter cubed, something the size of a car fender or something the size of an engine block, perhaps something the size of a engine wing or an airplane wing. So let's call this really big parts. Airplane wing. House. Bridge. Etc. And there are additive demonstrations of really big parts already. There's some really interesting bridge printing going on in Europe where they basically bring the 3D printer to the side of a canal and they 3D print a plastic bridge right over that canal. So that's cool. Of course, everyone's seen 3D printing of houses using concrete printers, and Oak Ridge and the folks that are developing BAM have made some airplane wings or trim tools for airplane wings, which is basically a jig for an airplane wing out of additive manufacturing. So those are big parts. They're not really industrialized yet, but parts in the range of 1 kilogram or 1 liter, there's a lot of those made. And so in general, we're talking about how do you industrialize components that are sort of tabletop size, or components of larger systems like an alternator for a car or something like that. So most of the discussion that we'll have is on parts of this size. There are bigger parts being printed, car fenders, larger demonstration pieces, but these are less common just because there aren't many printers that can handle this size of part. So there's not many printers out there right now that have build volumes of 3 feet on a side or a meter cubed. And so mostly we're talking about the smaller stuff. Even the industrial scale printers that we've seen, in general, they're printing a bunch of components at once. And so we'll continue to talk about this, but this gives us an idea of when they talk about industrializing additive manufacturing, sort of what scale are they talking about? So we're not printing the house yet in a way that will work for consumers, but we are printing things like brackets. We are printing things like shoes. We are printing things like dentures. You know, a lot of the examples we've talked about sort of fall into this category. You know, the other technology is being developed. So that's sort of the scale, and we can continue to talk about the scale. And I think that's one of the interesting things that you might want to think about for your final project. You know, when you talk about printing peak, what kind of parts are we talking about? Or when we talk about printing continuous carbon fiber composites, you know, those are really useful for things like airplane wings or turbine blades. And so thinking about what size the object has to be or what's possible, I think is an important part of this discussion. But in general, we're at the smaller scale right now. Any more questions or more discussion on this? Great. All right, Eddie. Thank you very much. I see your chat. Okay. So this is one of the papers from the collection, and we're just going to walk down through a couple of the key papers and a couple of key results. So you can see that, you know, it's not just like Hickner saying that additive is more sustainable, or I read on a web page, and of course it depends where that web page is from, that additive is more sustainable. But people are writing peer-reviewed papers on this and really making arguments as to why or why not this is the case. And what's interesting is that they're developing methodologies to analyze this. So it's not necessarily the conclusion that's the most important, because additive technology is still being developed, but it's the methods that groups are using to do the evaluation that's going to be portable to new technology or new materials or new ways of thinking about manufacturing. And so that's interesting, because whether or not the conclusions are 100% true, the methodology is useful for taking whatever next step you're interested in. So anyway, these folks are talking about additive and the environmental components of additive manufacturing and how that might be different than traditional manufacturing. Because of course we think of traditional manufacturing, you build a big factory, there's waste. Of course, there's a lot of industrial waste out there in terms of brownfields and Superfund sites. And so how might that be different in the age of additive? This is a cool chart from this reference. And they're talking about all these different segments of the industry. And we talked about this last time. Defense and aerospace, how big is that market? What's interesting about that market? Automotive, you know, $4 trillion in automotive. I certainly would not have guessed that the automotive industry was $4 trillion big. That's a big number. Healthcare and medical devices, you know, hundreds of millions of dollars, and then we have the rest. But if you start to think about sort of our industrial base in these buckets, you know, where is additive impacting now? So for defense and aerospace right now, and right in our immediate future, they are printing niche, low volume parts that are going onto airplanes right now. So whenever anyone gets to fly again, on Airbus parts and on Airbus airplanes and on some Boeing airplanes, there are additively manufactured parts on those planes today. And that's because weight reduction is a key component to make airplanes more efficient. And so one of the things that the airline industry has been going through is they would really like to increase the efficiency or the miles per gallon or the gallons per second, let's say, of their jets, because increased efficiency allows for cheaper operation, lower cost flights, less environmental footprint, and better routing because the planes, if they're lighter, can fly longer routes. And so weight reduction is a huge deal. Of course, with space flight, weight reduction is really, really important. And would just lump space in with defense and aerospace. And so people are doing additive right now in this industry because this is an immediate need. Same thing for healthcare. Right now, you can get some medical instruments and prosthetics for dentistry and some bone implants that are additively manufactured right now. So you can see, if you just run down this category, where is additive being used today in all these important industries? What's interesting about this chart is that in commercial and supply chain, two commercial segments or industrial segments that I don't think a lot about. Right now, there's a lot of printing bureau services. So Shapeways, Xometry, places like that where you can order 3D printed parts. Turns out that's a big business because not everyone who wants to have 3D printed parts has a 3D printer, and you can order some pretty nice parts from these places. So if you don't have a carbon printer, you can order a part that was printed on a carbon printer from Xometry. So that's cool. And that's a business right there. Some of these printing bureaus are big. They're multi-million or multi-tens of millions of dollars a year of business that they're doing. And in commercial, they're talking about intellectual property. They're talking about how to set up sort of how the additive industry is going to evolve in terms of competition and what the IP landscape is. And so that's very interesting. Likely developments. So this is probably what's going to happen. Right now, people are working on printing entire aircraft wings. So that's what the BAM folks are working on down at Oak Ridge. In consumer and retail, right now, you can design your own future craft 4Ds. At least you can pick the colors. And so that's co-creation with customers. That's starting to happen in automotive. You know, lightweighting is going to come into play and specialized components in some vehicles. So right now, Formula One and a lot of race teams already use additive manufacturing. And so that's happening, but that will come into consumer automotive soon. And so lightweighting, again, is important in automotive because of fuel efficiency. And we know that batteries in general are very near their limit of being able to stuff energy into a battery. And so the easiest way to increase the fuel efficiency of traditional internal combustion engine cars and to extend the range of battery electric vehicles is just to make them lighter. And so that's coming for additive in automotive. And then thinking about the future, you know, can you incorporate self-healing? When are we going to have 3D printing factories or rows of 3D printers? There's a couple of cool pictures that we've seen of 3D printing factories where they have 20 HP multi-jet fusion printers. That's cool, but that's not very common, so they're still working on that. And this actually might be a likely development, rows of 3D printers, because we already have hearing aids. We already have, in some cases, dental, and the people who make 3D printers are thinking about production cells and other things like that, where you can connect all of these printers together on the factory floor. So that's maybe coming a little bit faster than the authors anticipated. But this chart, as you go up and down the rows and as you go across from now to future, sort of gives you an idea of what the landscape of additive manufacturing is going to look like, depending on whatever you're interested in. I like this one too. In consumer and retail, grandparents buy 3D printers for themselves. That's funny. So additive is not only a young person's game and new technology, just like when I was growing up, it was a huge deal for someone to have a microwave, or microwaves were just coming into existence. And so, it took a while for people to adopt that new cooking technology, but it won't seem, just like additive manufacturing won't seem very new in the future. And if you've ever gone to uh, a retirement community, or some place where there's a significant number of older and wiser people, you see an awful lot of iPads in those places. And so the grandparents can be early adopters in some cases. All right. So this is another way to think about this. And again, I just want to put up some charts from this paper so we can talk about benefits and weaknesses of additive manufacturing compared to conventional manufacturing. Because sort of in this class and in some of the other additive classes, and even in research, we say, well, additive is great, it's the future, let's just do additive because it's awesome. And I agree with that because I like to do additive manufacturing. But if you're working at a company and the company is existing to make products and make money, you really need to compare additive to conventional manufacturing. And so we really can't lose sight of conventional manufacturing processes and how they compare, because conventional manufacturing is mostly how we get stuff today. And there's a lot of good industry out there. There's a lot of industries making money, and there's a lot of industries selling conventionally manufactured products that lots of people are buying. And so we always need to compare additive to conventional manufacturing. Of course, one thing that we can think about is additive manufacturing enables to make things that can't be made otherwise. So that's always a plus. That's really interesting. But, that's still a niche that has to be defined based on exactly what the component is. And so you can read this. I'm not going to go through it too much, but you see right here, less waste. Well, in some cases that's true. In some cases it's not true. It's right in the middle. And so if we're thinking about the environmental impact of additive manufacturing, in some cases additive has less waste than traditional manufacturing, but that's not always true. So it needs to be analyzed. Certainly weight reduction, we already know from topology optimization, you can make lighter weight parts with additive in a lot of cases than you can with conventional manufacturing. And that's why aerospace was an early adopter of additive. It's not that planes were expensive and so you could just make more expensive stuff. There was a distinct advantage of additive manufacturing in the aerospace community in terms of weight reduction. So they did it because they could see the payoff. They said, well, if we save 1 gallon of fuel per flight, this is going to be the payoff, and so we can invest, because the return on investment calculation told them that if they adopted additive, if they spent the money to adopt additive, it would pay off. And so in some cases, when we ask the question, should you do additive, the answer is, what is the return on investment? Or what's the net present value of buying this printer, or what's the payoff period? There's a lot of ways to express ROI, but that's really how industries decide to do something or not. And so weight reduction has a big return on investment in aerospace. In automotive, weight reduction is a likely development, but it's not as big of a factor. So you can decrease the weight of a car and it just increases the fuel efficiency a little bit. But people buy cars for lots of different reasons, not only fuel efficiency. And so the return on investment is different, or the payoff or payback is different in automotive than aerospace for weight reduction. So that's interesting. And that's why some industries adopt AM on a different time scale in different places than other industries. Fewer spare parts is definitely a plus. And then you have some negatives, right? You have limited part dimensions. We just talked about that. Additive can only make so many parts. In a lot of cases, you have lower surface quality. So if you're going to FDM something, that's a negative compared to traditional manufacturing. So all of these things, and you can look at lower dimensional accuracy, et cetera, all of these things really go into the comparison of additive to conventional manufacturing and gives you at least a framework, whether they're right or wrong about these different issues for different industries. It gives you a framework to think about the pros and cons of additive. Any comments on that? Any questions? All right. So in this paper, what they talked about was the specific energy consumption, or this on the x-axis. So this is in megajoules per kilogram. So if I'm going to make a component that's 1 kilogram, how many megajoules is that going to take? And they talk about this energy consumption for all the different additive processes here. So if I'm going to do stereolithography, you see that the energy consumption is rather low. And they have all the references here, and you can go find those references if you want. If I'm going to do metal deposition, either laser directed deposition or direct metal laser sintering, things like that, or electron beam melting, I have a different specific energy consumption, or specific, of course, just means per mass. And so that's interesting. Polymer processes like stereolithography tend to be on the low end, and metal processes tend to be on the high end, although that's not completely true, because you have selective layer melting and selective layer sintering occupying a given band, and there's still an order of magnitude difference between 51 and 500. But the energy consumption gives you a way to think about the impact of the manufacturing process on things like emissions, eventually on things like cost, because as you're making part after part after part, it's raw material cost and energy cost that might matter. And so this gives you a way to think about energy consumption for additively manufactured processes. And then what's really cool about this paper is that they talk about all the different energy consumption aspects of making a given component. So how much energy does it take to make a tie alloy? So you see this component here is made out of titanium alloy. And it turns out there's a lot of energy that's needed to refine titanium to industrial quality that then you can do additive manufacturing on. So you see that the energy required to produce raw titanium feedstock is big compared to, energy needed to do AM. So even though we have the energy budget for different AM processes here, at least in the case of titanium alloy, you see that this bracket takes a lot of energy to make that titanium in the first place. In general, for metal alloys, that's true. And so actually, the production of the raw material has a huge cost, and that's why people are interested in more sustainable materials. Or can we use plastic instead of metal because it doesn't take as much energy to refine, or doesn't take as much energy to synthesize plastic as it does to refine titanium. And so this just breaks it down a little bit. Of course, you have a little energy for distribution, etc. But in some cases, we call this embodied energy, or the intrinsic energy that's needed to get the component that we want. So not only is it all like the shipping and the energy required to run the additive manufacturing factory, it's the energy required to do the refining, to do the mining, to ship that ore where it needs to be refined. And that embodied energy can be an important component, especially in lots of metals. And this is why metals need to be recycled, because it's so much energy to refine that metal in the first place. So the most important thing you can do in terms of recycling is make sure your aluminum cans are recycled, because aluminum has a really high embodied energy. It's nice to recycle the plastics so they don't wind up on the side of the road or in the ocean, but the environmental footprint in terms of energy of plastics doesn't compare nearly to the environmental energy footprint of aluminum. So that's very interesting. And that's broken down in this paper right here. Any questions, any comments that people want to talk about? Okay, like I said, this is getting in the weeds a little bit, but hopefully it rounds out your education here in the latter part of the semester to think about some of the bigger issues of AM and how those might dovetail with your interest, and also dovetail with some of the stuff that we learned about the nitty-gritty of AM composite and polymer materials. And so in this reference right here, again, thinking about environmental benefits and about environmental concerns, what are the pros and cons of mass production versus mass customization? What can be done in terms of personal fabrication versus mass fabrication? Why is this important? What are some of the larger issues around manufacturing when we compare different types of production? So I'll just let you think about this. And like I said, it's not necessarily that these folks have the perfect picture of what's going on, but the orderly analysis and some of the analysis tools that they use to think about additive, I think will be useful to you in the future as you begin to think about what additive means to larger industries. And so when you think about AM and you think about how AM again fits into the pros and cons, the benefits, why is AM important? Lightweight for aerospace components, that's a benefit. We know that's true. Additive is happening in healthcare. So if you want to do additive, or if you want a job in additive, or you want to be successful in additive, this is a way to sell it. So you go work for Stryker, who makes biomedical devices, and you say, there's a way we can additive this to add value and to differentiate our products versus other folks. And that in general will be successful. Or if you go work for Boeing and say, we can make these components lighter weight and just the same quality and strength as the components we currently make, that's a success. And this is where AM is being adopted. In a lot of the things that we've talked about, there's this big uncertainty. There's no mistake why uncertain is bigger than yes or no, because we just don't know how important is lightweighting going to be in cars. It's likely going to move this direction, especially if we don't have any breakthroughs in batteries, but it's on the cusp. It's likely, but we'll see. There's other things, spare part production, probably, but it needs to be demonstrated. It needs to be for the right things. Decentralization of manufacturing, that's always pointed to as a benefit for additive, but it still needs to be proven. But we know things are going to be very difficult for additive if you try and do mass production, especially versus conventional manufacturing. Or substitution for similar parts. So right now we injection mold toothbrushes. If you start a company that says, I'm going to 3D print toothbrushes, you better have a very specific value proposition to be able to sell those toothbrushes, because it's not clear if people are clamoring for customized toothbrushes that they'll pay triple the price of. It is clear that some people will pay a lot more for customized shoes, but that's because shoes are a luxury good, or shoes are a consumer good that has an emotional component to it. Just like we talked about the customization for cars, where they have a splash light or something like that. And I forgot to put up that mini link, but I'll find that and put it up. But you need to find the niches for additive where you can really demonstrate to the consumer where it's going to be valuable. And so this gives us a way to think about that. Any questions on charts like this, trying to think about, what's right about this type of analysis, where this analysis might fall flat, something that, is not super clear to you, or any comments in general that people want to make? All right, well, this gives us something to think about as we take a little break next week, and so you can think about the larger ramifications of additive. But let's keep going. So this paper discusses the sort of energy comparison of AM and traditional manufacturing processes. Here's the reference right here. We saw a little bit on the energy in the last paper, but I'm just going to show one plot from this paper. And it's interesting because it gives you a broad landscape of all the different manufacturing processes and the rate. So kilograms per hour, whether it's something like injection molding or something like a cupola, and a cupola is way out here, and that is steel refining. So when you're doing metal refining, you have very high rates of that versus injection molding, where injection molding will fall right here, where you can do on the order of 100 pounds per hour in a specific injection molding machine. And there's all sorts of things like binder jetting. So if you're going to do binder jetting, what's the production rate? If you're going to do FDM, just in terms of kilograms per hour, and this is per machine, how many kilograms per hour of material can you deposit in a given process? So we have, I just saw BAM right here. So here's material extrusion, AM, in terms of BAM. So BAM, you can put down on the order of 10 or 20, of course this is a log scale, kilograms per hour. So you can do significant deposition rate. And in some cases, manufacturing is all about how fast can you deposit a given mass of material. Of course, you need the shape, you need the dimensions, you need all the things that you care about in terms of producing a component. But if you're trying to do high rate production with a process that can only deposit 50 grams of material per hour, that's going to be difficult, because in some cases, the high volume scales directly with the deposition rate. And so that's interesting. And then this is plotted, that's interesting in and of itself. What's the process rate for all these different processes? But that's plotted against the energy requirements for the different processes. And this is where it's really interesting to compare additive processes. And so in terms of how many joules per kilogram are required for BAM or for FDM or stereolithography. So it goes back to something like this, even though this is in megajoules per kilogram, this is just in scientific notation. So it's in the same ballpark. But now you think about, okay, how much energy is it going to take per kilogram and how fast can I deposit it? So when you're way down here, in terms of, let's say, EDM processes, electrical discharge machining, if you're going to do semiconductor processing, so that's right here, those are really low rate processes because you're not moving very much material, and they cost a lot of energy per kilogram. But now we have stuff like powder bed fusion, right here, low energy, reasonable scale. We've got material extrusion, AM, BAM, even lower energy per kilogram, but high rate. And we can compare that to all sorts of other sputtering technology, water jetting. Here's water jet. So if we're going to cut parts out, I think water jet is this funny symbol right here. So it often takes some time decoding exactly what these things are. But this gives us a way now to frame additive manufacturing against conventional manufacturing in terms of energy requirements and process rate. And both of those are interesting in and of themselves. And so if you're more interested in these issues, of course, you can read this paper and they discuss why this is the way it is and what the limits are. So if you're interested in decreasing the energy of AM even more, they'll say that, well, AM compared to these large scale processes, maybe this is as low as you can go in terms of processing materials. So, 1 times 10 to the 6 joules per kilogram is about as low as conventional manufacturing gets and about as low as BAM gets in terms of the energy requirement to process a material. So maybe you don't have to worry about the energy efficiency of most AM processes because they're in general on the lower scale. And so it might not be that the innovations are in the energy consumption. What it might be is that trying to push out this process rate. And we go back to small components versus big components versus really big components. Where AM really suffers in terms of manufacturing is that it's really hard to deposit a lot of material quickly in the shape that you want. And so we see that with stereolithography or with powder bed fusion or especially material extrusion AM. It's just really slow to build some of these components compared to conventional manufacturing. So maybe increasing the process rate, increasing the build size, increasing the deposition rate is exactly what additive needs to move all the additive points right here a little bit further down the curve. Any questions on that? Okay, a plot like this is worth looking at, and of course there's all the references in there, but this is interesting to think about in terms of large scale AM and what some of the comparisons are. So this, I think, is the last paper we're going to talk about in this series. And so I just wanted to bring this up because they have a really nice case study for injection mold tooling. So we've talked about this before, and we've talked about how additive can be used to not only make components that you sell. So I'm going to additive a shoe sole and I'm going to sell that. But this is the case of making a tool that helps you make something. So making an injection mold, we know, is difficult. It takes a long time. You have to machine that. And that's often the slow step in terms of design iterations. And also, once you have an injection mold and you're making toothbrushes, no one really wants to change it. And so you don't, when you're injection molding a component, it's hard to customize. No one really wants to change the mold. It's really expensive to do that. And so if you work in the injection molding industry, the issue of the molds or the cavities in which plastic is injected into is a real big issue for the community. And so this paper is a nice case study of what are the environmental and economic benefits of additive manufacturing on this specific topic. And this is relevant to polymers and composites because most polymers and composites, or many of them, are fabricated using injection molding. So again, it takes some time to pick apart these plots, but this is interesting to think about. So first, let's look at the numbers. Conventional manufacturing, onshore, and overseas. So if you're going to outsource your mold making overseas into a lower cost market, offshore versus onshore, I think this is written from the perspective of the US because it was published, I think, in a Yale journal. And so onshore refers to manufacturing in the US. And then you have additive manufacturing current. So what can you do with AM today? And what's possible, we think, with AM in terms of mature technology, which it's not just yet. So if we look at lead time, something that's easy to understand, and we look at offshore versus onshore, it's going to take a little bit longer to get that mold made, say in China, or to be made in Eastern Europe, where the machining costs are lower compared to making it just down the road, say in Erie or something like that, where they have a lot of mold making. So you can get it faster if it's onshore, and in some cases, it's going to take just as long to get that thing additive today because there aren't lots of places that do additive. So if you wanted to order a stainless steel injection mold right now made using additive, it's going to take a little while. It's going to take a couple of months in their estimation. So this is 9.3 weeks in order to get that done because there isn't a good supply chain for making molds or for making steel molds using AM. But it's coming because as soon as AM mold making is mature, you can get that mold in a month or so. And so that's interesting to think about the difference between what's possible with AM versus what you can do with AM today. And the same thing for energy consumption, greenhouse gas emissions, which is important and is in some ways linked to energy. And then you have cost, which is about what's the investment that you need to make right now. And so there's a couple of interesting aspects to this. And so there's margins, there's labor, there's energy, there's things like that. But you see that all of the ways to make molds right now, whether you're going to do it offshore, onshore, or you're going to do it additively, are within the realm of being the same. Even additive is a little bit higher cost because additive is not mature in this space. Like for instance, we have an injection molding extruder on the ground floor of Steitel. So that's great. I have an injection molding machine. I've got plastic. I can go do injection molding. But if I wanted an additively manufactured mold for that, it would take me a while and it would cost about the same or even more than it would take me to just order an injection mold from a traditional mold supplier that uses machining. And so when people talk about additive manufacturing tooling being faster and cheaper than conventional tooling, what they're mostly talking about is future benefits. So the matured performance of additive, you see a big benefit here, half the cost or less, or even way less than the traditional way to manufacture these components right now. And so oftentimes we're talking about future benefits of additive, not necessarily the thing you can do just today. Now, I can order a plastic mold that I can use for a couple of injections right now. So Stratasys will make me a high strength plastic mold that I can use for injection molding, but that's not a permanent tool. That's not a metal mold that I can use to make thousands or hundreds of thousands of parts like I can with a stainless steel mold or something like that. So again, this gets to the promise and in some cases the hype of additive manufacturing, that oftentimes we really focus on what's the future benefit, whereas if you wanted to do this today, it's going to be a struggle. It's going to be just as long, it's going to cost just as much money as a conventional process. And so we need to get over this, and we need to keep developing additive manufacturing to push on some of these issues. And at least for this specific case study within these specific parameters that this group studied, I think that this is pretty reasonable. Any questions on that? All right. Same thing goes for payback. So payback goes right into the upfront cost, and then the cost per part. And so that's all interesting. And you see that in general, the future benefits of additive are the ones that's touted, but the current state of affairs for additive is it's on par, or in some cases worse than conventional manufacturing, just because of supply chains and the ways of doing things are not well known. So if you go to a mold making shop right now and say, I'd really like to have this mold additively manufactured, they'd be like, oh, we don't do that very often. We've thought about it. Whereas if you said, I'd really like this machine, this mold machined using your conventional processes, they say, oh, great, we're ready to go. And so this is the bridge that we have to cross with additive that is just not quite ready for prime time in some cases. Versus for hearing aids that have already made the transition, the only way you're going to get a hearing aid nowadays is probably by additive manufacturing. There's very few hearing aids, I think it's less than 5% of the market right now, that are made the old-fashioned way, either by hand or with a custom mold. Most hearing aids are additively manufactured. So it's hard to get the conventionally manufactured part because the industry has already gone through the transition and they are already here. So there's some industries for which they're already at the matured performance of additive manufacturing, but not all industries are there. And so when we think about life cycle cost savings versus greenhouse gas emissions, so if we're saving cost, we generally have lower emissions reduction. So this is a hard axis to read because it's not, more emission reduction is good versus less emissions. And so this gives you an idea in terms of how life cycle really impacts what the greenhouse gas emissions are. And so when they're looking at these environmental and economic implications, in lots of cases, greenhouse gas emissions are one of the most important components of the environmental sustainability of the process. Because we're pretty good, we don't have lots of toxic waste anymore, although in some cases we do, and we're still cleaning it up. We're getting a handle on refuse and trash and other things like that, but greenhouse gas emissions, we certainly don't have any handle on right now. But the world is really thinking about this, and so poising the environmental footprint in terms of greenhouse gas emissions is something that people are starting to study, rather than, how many tons of material are going to go to the landfill per year or something like that. It's just another way to think about it. So what's interesting, especially in this special issue, remember what the special issue is that implications of additive manufacturing on the environment. Okay, so we can say additive manufacturing is cool, additive manufacturing is interesting, maybe it's got weight savings and supply chain issues, but it says that in this article, environmental benefit of AM in this tooling case is relatively marginal compared to the economic advantages. And so if you're doing additive for environmental benefits, it depends. Is additive a good idea for environmental benefit in this tooling case versus economics looks like it's going to dominate this case. So compared to the economic advantages, which are clear, so we look at this, the economic advantages of AM are clear, right? It makes sense to do AM for lower part costs in this case. But the environmental benefits are marginal. And so you need to think about what the case is, how this is important to whatever industry you're part of, and this methodology helps you get at the true benefit of the technology. So other than continuing to say AM is cool, AM is sustainable manufacturing, AM has environmental benefits, you can really start to dig into the weeds as to why this is important and interesting. And some companies and some industries are going to be focused on cost per part. That's a really important component of the automotive industry. And other industries and other places might be more focused on the environmental advantages. And so you also need to read the room and know who you're talking to in order to tell the story in a way that makes a lot of sense to your audience. So, you know, whether or not this exact analysis is airtight, it gives us ways to think about how AM is going to be industrialized. And a nice way to do that is through case studies. And we'll look at some other case studies in aerospace. We've already looked at some case studies in biomed to give us some ideas as to where AM is really gaining a foothold. And that's where we can look to innovations and what might happen next. Any questions on this? Okay, like I said, this is a little bit in the weeds from what we usually talk about. And if you want to go back to talking about polymers and polymer chemistry after break, just let me know. But I wanted to cover a couple of these broader things before we wrap up the semester. And so that was lecture 14. Let's go to lecture 15 slides, if I can find them here. Still don't know why Box orders things the way it does. But talking about some of these environmental and economic benefits, we just need to talk about manufacturing in general. So if we're going to do AM and manufacturing with AM, and basically working for a company, unless you work for a materials testing company, or unless you work for a research company or a university or a national lab, which are flavors of research companies, your company is probably going to be making something, is probably going to be producing something, and that's going to involve manufacturing. And so it's worthwhile to understand what manufacturing is all about and where AM fits into this overall picture. And we saw some examples of that in the previous lecture, and I just wanted to give you a little bit more information on this. So you have some tools to think about AM in the world of manufacturing. So 3D printing or additive manufacturing is already disrupting manufacturing in general. There's something called advanced manufacturing as well. And advanced manufacturing is just things that are not conventional manufacturing. So we already know how to cast steel. That's conventional manufacturing. But advanced manufacturing might be EDM. Or we already know how to do injection molding. So that's conventional manufacturing. But something like stereolithography is advanced manufacturing. So AM or additive manufacturing, and the acronyms are not going to be super helpful here. So advanced manufacturing is the big set of processes, and then additive manufacturing is a subset of advanced. And advanced manufacturing can be anything from more sensors, digital, more digital, different ways of doing conventional manufacturing that make it advanced. But when we talk about AM, we're going to talk about additive manufacturing because that's the topic of this class. But if you're an industrial engineer, there's a whole field called advanced manufacturing. Okay, anyway, we know prototyping is important, and they say in this reference, true, let me get that right, true rapid prototyping. And true rapid prototyping means you can prototype the finished part. So these are finished or near perfect functional parts. So in the past, in lots of design studios, in lots of machine shops, we had additive manufacturing to make mock-ups, to make models, to make demonstration pieces. That's rapid prototyping, but true rapid prototyping or production of functional parts is really where additive is excelling now. So you can additive something that can be used like a finished component. So it's a real prototype and it's ready to be tested rather than just a model that sits on a desk. You can also do design iteration. And so one of the things that's done when you're doing product design is what's called A/B testing. And this is what focus group testing is about. So you make two different products and you say, do you like sample A or do you like sample B? So whether it's two flashlights or two different phone cases or two different pens, whatever it is, they'll say, do you prefer this one or do you prefer that one? And they focus group those two things and survey people's ideas. And then they throw out the one that people don't like and they take the one that they do like, they iterate on that, and then they get another A/B test. So A/B testing is just a way to focus group products. And so this way you can get numerous functional prototypes. You can produce products or near finished products using AM that you just can't do another way. Because say you want to make two phone cases that are almost finished, how are you going to make those? They need to be machined. You can't injection mold them because injection molding is expensive and slow. And so how to produce just 100 or just 50 or 10 of something is important. And that really goes to low volume production. So you think about it, for AM right now, making 5 of something is easy, right? Making 50 of something, it's going to take a little while with your desktop FDM printer, but you can do it. And if you're going to injection mold, if you talk to an injection molding place, just to start, the mold costs $50,000. And so you need to amortize that over a lot of parts, and you need to buy an extruder and everything else. And so there's one of the challenges out there is how to make a couple hundred of something. And the military and other niche industries are very interested in this because this might be all they need in a year. And so how do you do this low volume production? We're almost out of time. This is where we'll pick up next time, but mass customization, that's really interesting. So how do you make 100,000 things that are all a little bit different? Inventory, spare parts, which we already talked about. And then how do you innovate when there's a lot of resistance? So if you have a conventional manufacturing process that works, how do you innovate against that? Because you already know how to make what you know how to make. If you already have an injection mold, there's not a lot of people who want to change that mold. So how do you do innovation in that stagnant manufacturing environment? Okay, we're just over time. I will open up the floor for any questions or comments here before we break for our stay-at-home Thanksgiving next week. Any questions? Okay, well, please put a little bit of thought into your papers and outlines, and you can submit those on Canvas anytime, so you don't have to wait until Monday after the break. And we will not have Zooms next week during Thanksgiving. Classes are off. And then we'll pick it up for the end of the semester and finish strong on some interesting stuff. And I'm happy to chat about projects, or if you really get stuck or if something gets off track, just let me know, but I'm around. Thank you very much.
Thank you.
Thank you. Have a good one.